Now, ionization energy. So first, let's look at the definitions. The first point, which is here, the ionization energy, i.e., of an element, is the amount of energy required to remove 1 mole of electrons from 1 mole of gaseous atoms of an element to form 1 mole of gaseous ions. Okay, so let's say example. This is the example. First, you have gaseous calcium atom. Then you change it to calcium plus, calcium positive gas. That means this is gaseous ions plus electrons. Okay, so everything is in gaseous state. You can see this is in gaseous state, this is in gaseous ions, gaseous state as well. So the thing here is, we know that calcium is basically metal. So metal is in solid. So we need to change calcium solid to calcium liquid to calcium gas. So of course, this process is something that we know, I think. So where this is melting, you have to melt the calcium, and then you have to boil it until it becomes gas, and then all these energies that involve to melt, to boil the calcium, all this energy are not ionization energy. So ionization energy are here onwards. So when you heat it some more, then the electron is released, plus electron. Okay, so only these parts are under the ionization energy. Okay, now of course all these they have a particular term for it, like enthalpy change of fusion, enthalpy change of vaporization. This is ionization energy. Change it to ion. Okay, so of course we standardize everything. 1 mole of this to 1 mole of this and 1 mole of this. So everything is under 1 mole. Then next point, ionization energies are measured under standard conditions, which are 298 Kelvin and 101 kilopascal. So it's under standard conditions. Okay, so the units of ionization energy are kilojoules per mole. So this is the unit for ionization energy. So this unit is quite common. Even like enthalpy change also, they use kilojoule per mole. Then the first ionization energy is the energy required to remove 1 mole of electrons from 1 mole of atoms of an element to form 1 mole of 1 positive ion. So you can see this is 1 positive ion. Then this energy is first ionization energy. So it is first IE. So if this is first IE, then we should expect calcium plus to calcium 2 plus to be second IE, second ionization, second IE. Okay, right, short form, IE. So you can see first ionization energy is this process. Second ionization energy is this process. Then you may feel like, okay, how about calcium? Okay, how about the more common situation? Calcium gas to calcium 2 plus gas plus 2 mole of electron. Then how are we going to count the energy? So that for this case, it's supposed to be the first IE plus the second IE. Okay, so it involves 2 processes here. So change to calcium plus, then change to calcium 2 plus. Okay, now let's see. Example, okay, this is first ionization energy. and then you can see IE1, first ionization energy, and then the value is positive 390 kilojoule per mole. So positive means endothermic. Endothermic, that means it requires energy. You need to have energy input to make this happen. Okay. Okay. Now let's look at trends in ionization energies. So ionization energies show periodicity, a trend across a period of the periodic table. Okay, so for example, let's see this. This is a cross period 2. So you can see the trend is like, in general, it is going up. But between certain elements, there are a going down trend, like beryllium to boron going down. Nitrogen to oxygen is going down. So in general, going up, except some exception over there. Okay. So as could be expected from their electron configuration, the group 1 metals have a relatively low ionization energy. Group 1 very low because it has only one valence electrons. To release that valence electron is kind of easy. So this is relatively high, of course, because this is noble gases. It achieves duplet or octet electronic configuration, which means it's full of electrons in the shell. So it is very stable. So that's why you need to release one electron. We require a lot of energy. Okay. Then we look at this. The size of the first ionization energy is affected by 4 factors. 4 factors. So first, the size of the nuclear charge. So that means how many protons. Basically, proton attract the electrons. So size of nuclear charge affect. Second factors, distance of outer electrons from the nucleus. So from nucleus to the outer electrons. So of course, the relationship should be obvious. So the greater the distance, then the lower the ionization energy. Meaning that if the valence electrons is very far away from the nucleus, then we can easily release it, as the nucleus could hardly attract the electrons that are far away. Let's come back to this one also. The relationship here, if the nuclear charge is high, then the ionization energy should be high. So should be common sense also, because nuclear charge will attract the electrons. So if they are strong, of course you need more energy to make the electrons release. And then next one, shielding effect of inner electrons. Shielding effect. So first we have to know what is shielding effect. So let's say I draw out sodium, let's say, for example. Okay, sodium. Sodium has 2 followed by A, followed by A, followed by 1. So this is sodium. What is shielding effect? Shielding effect is the electron at the inner shell repel the electron at the outer shell. You know, electrons basically they are same charge. They are negatively charged. This is also negatively charged. So shielding effect is basically the repulsion of the inner electron on the outer electron. So it is greatly affected by affected by the number of shells. So imagine if there is a shell here, so this one will have shielding effect on the outer electron. So this shell also have shielding effect on the outer electrons. So the first shell repel the electron, the second shell also repel the electrons. So in other words, it means the greater the number of shells, then the greater the shielding effect. So okay, shielding effect, right? How it affect the ionization energy? So it's like this. When we have a greater number of shells, then we have a greater shielding effect. Then we have, shielding effect is repulsion. If they repel a lot, then these electrons, the outer electron, can release more easily because this one repel it and make it able to go away easily. So the ionization energy is lower. Okay. Then we have last factor, spin pair repulsion. Spin pair repulsion. So in the orbital, let's say let's say 3s orbital. Okay. So you can see the electrons are arranged in this particular way. One have arrow pointing upwards, one has arrow pointing downwards. So of course, we discussed this before by using right hand grip rule with your thumb pointing upwards. Then the forefinger twist. Twist in what way? Twist in a way that is anti-clockwise. So this is clockwise then. So they have repulsion also, although they have minimized the repulsion, but repulsion is still there. Okay, so it spin pair repulsions. If it is big in spin pair repulsion, then ionization energy will be small. Okay, so another example is if you have orbitals that are singly filled, the repulsion is lower. Oops. Okay, the repulsion is lower. If the electrons are paired up, then there are spin pair repulsion. So spin pair repulsion happens on that particular orbital. Spin pair repulsion is higher, and then IE is lower. Okay, so now let's see what else. First ionization energy. First ionization energy increases across a period and decreases down a group. Okay, down a group, let's say for example group 1. So you can see lithium, sodium, these two are group 1. We can't see clearly, but what happened is the ionization energy decrease down group 1. Okay? So logically it is because there are more and more shell. When you go down group 1, more and more shell, then the shielding effect is getting greater and greater. Then the ionization energy decreases. Okay. Going across the period, it increase. Ionization energy increase. Going down the group, ionization energy decreases. So these are the two trends. Okay, so it's important, the two trends. Yeah. So the first one, increase across the period, decrease down the group. Okay, so let's move on. Okay, now let's see here. Ionization energy across a period. So what they say here, the ionization energy across a period generally increases due to the following factors. Generally increases, although they are going up, down, and then up, then down again, and go up again. So in general, it's still increasing. So we need to know how to explain it. So across a period, the nuclear charge increases. Imagine there are more and more protons. Okay, so more protons. Yeah. Then after that, this causes the atomic radius of the atoms to decrease. So more and more protons mean they attract the electrons and making the shells to be closer to the atoms and making the atomic radius to be smaller. So as the outer shell is pulled closer to the nucleus, so the distance between the nucleus and the outer electrons decreases. So try to imagine on this also. They attract the shell, and then the shell becomes smaller or become closer to the nucleus, and hence the radius is smaller. And then the shielding by inner shell electrons remains reasonably constant. Shielding is affected by how many shell. So the number of shell doesn't change over here across the period. They have the same shell. So for example, like period 3, across period 3, so they have 3 shells. So all the way across the period, so 3 shells. So same number of shells, shielding effect is constant, more or less constant, as electrons are being added to the same shell. So the important idea here is, if you have same number of shells, then shielding effect is more or less the same. Okay, then we continue. It becomes harder to remove an electron as you move across a period. So of course it's harder, because there are more and more protons, right? So across the period there are more and more protons. So more energy is needed. So ionization energy increases. So this one, more and more protons. Okay, now let's see the special scenario there. We have, if you still remember the situation just now, we have in period 2. In period 2, we have lithium, which go up, then beryllium, then after that boron. So there is a dip in the trend. So beryllium and boron, there is a dip over there. So after that, they go up again, and then go down and go up again. So there are 2 dips over there. So we need to understand why there is a dip here. So there is a slight decrease in first ionization energy between beryllium and boron. Beryllium, boron. As the 5th electrons in boron is in the 2p subshells. 2p subshell. Okay, let's try out. Beryllium is basically 1s2, 2s2. And then boron is 1s2, 2s2, and 2p1. So the first ionization energy remove electron from 2p, and for beryllium, the first ionization energy remove electron from 2s. So this is obviously further away from the nucleus, and this is more easily to be removed compared to this one. This is closer to the nucleus. more attractions between the electrons and the nucleus. So this is harder to remove. More energy is required. This is easier to remove. So that's why there's a drip here. Okay, there's a dip over there. Okay, so now let's see. Okay, they say boron has the 5th electron in the 2p subshells, which is further away from the nucleus compared to the 2s subshells of beryllium. Beryllium, the electrons is in the 2s subshell. Okay, so for boron, the first electron to be removed is in the 2p subshell. Okay, and then further explain it. Beryllium has a first ionization energy of 900 kJ per mole, as its electrons configuration is 1s2, 2s2. Boron has a first ionization energy of 800 kJ per mole, as its electron configuration is 1s2, 2s2, and 2px1, which is this situation. So easier to remove, then less ionization energy. Now the second dip is here, so which involve 2 elements. They are nitrogen and oxygen. Nitrogen, oxygen. So okay, I go through. So lithium, beryllium, boron. After boron is carbon. After carbon is nitrogen. So after nitrogen is oxygen. After that, fluorine. Then neon. Okay, so there is a dip here, nitrogen and oxygen. So we want to know the reason also. Okay, so there is a slight decrease in first ionization energy between nitrogen and oxygen due to spin pair repulsion in the 2px orbital of the oxygen. So let's think about it. Nitrogen, right? Nitrogen is 1s2, 2s2, 2p3. 2p3. This 2p3 is like 1, 2, 3. Oxygen is 1s2, 2s2, 2p4. And the 2p4 is like 1, 2, 3, 4. So this is where the spin pair repulsions happens. They pair up already. The electrons start to pair up. So spin pair repulsion happens. So this particular electron, because of repulsion, you can remove it more easily compared to this one. No spin pair repulsion here. This one, spin pair repulsion happens. Okay, so nitrogen has a first ionization energy of 1400 kJ per mole, as its electron configuration is 1s2, 2s2, 2px1, 2py1, and 2pz1. Okay, so which is like this, singly filled. Oxygen has a first ionization energy of 1310. You see, which is lower because of the spin pair repulsion, as its electronic configuration is 1s2, 2s2, 2px2, 2px2, which is this one, pair up already, 2py1 and 2pz1. So, whenever you explain ionization energy, you have to write down the electronic configuration. So you have to write down something like this. To write down, then you explain afterwards. Okay. So in oxygen, there are 2 electrons in the 2px orbital, which is this orbital. So the repulsions between those electrons makes it slightly easier for one of those electrons to be removed. So easier to remove because of the spin pair repulsion. So easier to remove, then ionization energy is lower. Okay, so from one period to the next. Okay, let's say from period 2 to period 3. Okay, so there is a large decrease in ionization energy between the last element in one period and the first element in the next period. Okay, so what they're trying to say is, let's say I give you one example. Okay, let's say now the large decrease. So I'm going to put example. Okay, so the example is going to be neon, the last of period 2, to sodium, the first of period 3. So there is a large decrease over here. Okay, so the reason is written there. Okay, of course, to know the reasons, let's write down the electronic configuration first. Neon, 1s2, 2s2, 2p6. Sodium, 1s2, 2s2, 2p6, 3s1. If you look at the outermost orbital with electrons, so you will obviously understand why. Because the first electron to be removed comes from 3s1, which is further away from the nucleus. This is nearer to the nucleus, and some more this is fully filled, which is stable. Okay, now let's see how they explain it. This is because there is increased distance between the nucleus and the outer electrons as you have added a new shell. So this to this, from 2 shells to 3 shells. This one 2 shells, 1 and 2. This one 3 shells. So the last electron stay in the third shell, which is increased in distance from the nucleus. And there is increased shielding by inner electrons because of the added shell. So the shielding effect is very much happening here in sodium because there are 1, 2, 3, there are 3 shells. So the 2 shells inside will repel the third shell. These 2 factors outweigh the increased nuclear charge. So that means although there is increase in proton number by 1 unit, but the effect is not much compared to the shielding effect and the distance. Okay, so now let's see ionization energy down a group. So let's say, for example, group 1. So lithium, sodium, and then potassium, and so on. Okay, so group 1, lithium, sodium, potassium, and so on. Obviously, this is small, this is bigger, and this is the biggest out of these 3. Okay, so they are bigger and bigger. Of course, we should expect the valence electron, which is staying further and further away from the nucleus. So, for example, potassium, it has 4 shells. So, very much away from the nucleus. The outermost electron is far away from the nucleus, so can easily remove it. Yeah. So let's see here. The ionization energy down a group decreases due to the following factors. So first, the number of protons in the atom is increased. So imagine, which is true, more and more protons when you go down a group. So the nuclear charge increases. So it should be reasonable here. Going down the group, nuclear charge increase. Then you're wondering, if nuclear charge increase, then how come you need lesser and lesser energy to remove electron? Okay, so there are other reasons which outweigh these factors. But the atomic radius of the atom increases as you are adding more shells of electrons, making the atoms bigger. So adding more shells. So the distance factors come here. So the distance between the nucleus and outer electrons increases as you descend the group. So we always play around with the four factors, so the nuclear charge, the distance, the shielding effect, and the spin pair repulsion. Okay, so we have to talk about these four factors. Whoever involved, you just talk about it. Okay, now the shielding by inner shell electron increases as there are more shells of electrons. Which is true, there are more and more shells. So from 2 shells to 3 shells to 4 shells. So more and more shielding effect. This factor outweighed. So the shielding effect and the distance, these two factors outweigh the nuclear charge. Okay, so meaning it becomes easier to remove the outer electrons as you descend the group. So the ionization energy decreases. Okay, so now let's see. Ionization energy trends across a period and going down a group. Okay, this is the conclusion. So across a period, increases. Increase in nuclear charge. Number of shells is the same. Shielding effect is the same. Decrease atomic or ionic radius. The outer electrons is held more tightly to the nucleus. Typo error, to the nucleus, so it gets harder to remove it. So explanations are all given in this way. Okay, now down a group, you see the explanation. Increases in nuclear charge. Number of shells increases. Distance of outer electrons to nucleus increases. Shielding effect increases. Therefore, the attractions of valence electrons to the nucleus decrease. So, increased atomic or ionic radius. The outer electrons is held more loosely to the nucleus, so it gets easier to remove it. So, you can see the distance and the shielding effect outweighs the nuclear charge. So making the ionization energy decreases. Now, ionization energies, the trends. So they say ionization energy shows periodicity, a trend across a period of the periodic table, as could be expected from their electronic configuration. The group 1 metals have a relatively low ionization energy, whereas the noble gases have very high ionization energies. So this is the general trend. Group 1, very low. Group 18, or the noble gases, highest in ionization energy in the same period. So the size of the first ionization energy is affected by 4 factors. Okay. Size of the nuclear charge, this is the first factor. So the nuclear charge increases with increasing atomic number, which means that there are greater attractive forces between the nucleus and electrons. So more energy is required to overcome these attractive forces when removing an electron. So that means proton has the effect here. More protons, more attractive forces, harder to remove the electrons. Okay, next factor, distance of outer electrons from the nucleus. So electrons in shells that are further away from the nucleus are less attracted to the nucleus. The nuclear attraction is weaker. So the further the outer electron shell is from the nucleus, the lower the ionization energy. So again, they talk about the trend in this way. This one, they said if nuclear charge is high, then ionization energy is high. This one, they said if the distance is high, then the ionization energy is low. Okay, then the third factors, shielding effect of inner electrons. The shielding effect is when the electrons in full inner shell repel electrons in outer shells, preventing them from feeling the full nuclear charge. So the more shells an atom has, the greater the shielding effect and the lower the ionization energy. Okay, so they are trying to say that if the shielding effect, okay, it is the shell first. If the shells increase, then the shielding effect is big, and then the ionization energy is low. Spin pair repulsion, the fourth factors. Electrons in the same atomic orbital in a subshell repel each other more than electrons in different atomic orbital, which makes it easier to remove. So they are trying to say electrons in the same atomic orbitals, which means electrons in the same orbital is something like this. Spin pair repulsion happens more here. Okay. So more than electron in different atomic orbital. Different atomic orbital is like different atomic orbitals is like this. This is different atomic orbital, less repulsion. So this one more repulsion. So which make it easier to remove an electron. So you can remove this more easily because of spin pair repulsion, which is why the first ionization energy is always the lowest. Okay, and then so the first ionization energy increases across a period and decreases down a group. So they come back to the same conclusion again. Okay, so and they come back to the same graph again. Okay, so you can see across the period generally increases. Down the group, this to this generally decreases. Okay, so let's move on. Okay, now let's see this. Okay, ionization energy across a period. The ionization energy over a period increases due to the following factors. Across a period, the nuclear charge increases, more and more protons. This causes the atomic radius of the atoms to decrease. So, first factor, nuclear charge. Second factor, the distance. As the outer shell is pulled closer to the nucleus, so the distance between the nucleus and the outer electrons decreases. Distance decreases. The shielding by inner shells electrons remain reasonably constant as electrons are being added to the same shell. So the third factor, same. It becomes harder to remove an electron as you move across a period, so more energy is needed. Ionization energy increases. Okay, so this one is just repeating. There is a rapid decrease in ionization energy between the last elements in one period and the first element in the next period because there is increased distance between the nucleus and the outer electron as you have added a new shell. This one is repeating also. This is between the neon and the sodium that I gave just now. So neon has 2 shells, sodium has 3 shells. So increased distance. So that is increased shielding by inner electrons because of the added shells. So sodium has more shielding effect. And these two factors outweighs the increase in nuclear charge. Okay, now there is a slight decrease in ionization energy between beryllium and boron, as the fifth electrons in boron is in the 2p subshells, which is further away from the nucleus than the 2n subshells of beryllium. So there is a dip in the period, so they're repeating again. Okay, so this is beryllium 900, boron 800. Okay, now the second dip, nitrogen and oxygen, there is a second dip because of the spin pair repulsion. Nitrogen is 1400, no spin pair repulsion. Oxygen is 1310, spin pair repulsion happens here. The atoms, the electrons are in the same atomic orbitals. So repeating information. Now let's move on. Ionization energy down a group. So the trend is decrease. Decrease. Why decrease? So the reason, first, the nuclear charge increases. More and more protons when you go down a group. The distance also increases. Imagine going down the first group from lithium to sodium to potassium. So potassium is the biggest in size. So there is a increase of distance between the nucleus and the shell, between the nucleus and the outer electrons. Shielding increases. Shielding effect increases because the number of shell increase, and then this factor outweighs the nuclear charge, so easier to remove the electrons. So ionization energy decreases. This one is repeating. Okay, now let's move on. Okay. Across a period, increase. Down a group, decrease. Okay, so this table we have just gone through. Now let's move on. Successive ionization energies of an element. This is different already. Successive ionization energy of an element, right? Refer to the same elements, for example, same element. So like calcium. Calcium, to remove the first electrons, you have to take it from 4s1. So it's kind of easy, low IE. So to remove the second electrons, you have to take the, oh no, this is not to be in that way. Okay, calcium should be like this. Calcium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. That is calcium atom. So to remove the first electrons, you take it from here. Easy. To remove the second electron, you take it from here also, which is still kind of easy. Okay? But the thing is, ionization energy, the second ionization energy come to 1150 already, because something like this. Calcium to calcium plus to calcium 2 plus. So the first IE remove 1 electron. The second IE remove another 1 electron. This is harder because calcium is already positively charged. So you want to remove 1 electron that is negatively charged. That is harder because there are attractions between these two. Attraction. So that's why this is 1150. If you want to remove the third one, it is much harder. The third one, right? You see the first and the second come from here. The third one come from here, which is very stable. They achieve octet already. 8 valence electrons. They achieve octet. This is much harder. So that's why you can see many times increase over here. And then the fourth one is still from here. So this and this not much different. Okay, let's see how they put it in words. Okay, you can see here. The successive ionization energy of an element increase. So you can see increase. Must refer to the same element, and you keep removing electron from the same element. That is called successive ionization energies. So it is increasing. So this is the trend. This is because once you have removed the outer electrons from an atom, you have formed a positive ion. Something like this. They form positive ion already. Positive ion can attract electrons. Okay? So removing an electron from a positive ion is more difficult than from a neutral atom. This one neutral. Remove it easy. No attraction. this is positive ion, remove it harder because attractions. So as more electrons are removed, the attractive forces increase due to decreasing shielding and an increase in the protons to electrons ratio. So if you keep removing electron, right, so the number of shell decreases from 4 shells to 3 shells. So shielding effect decreases also. At the meantime, the proton to electrons ratio also increase. So the attraction is getting stronger. So the increase in ionization energy, however, is not constant and is dependent on the atom's electronic configuration. So you don't expect that the increase in a straight line. So they are increasing slowly, then in a sudden increase a lot, then increase slowly, then in a sudden increase a lot. So we will have table to see after a while. So this is everything about calcium. Let's move on. Okay. So you can see the graph here. Okay. To remove electron from 3p, so the ionization energy increase slowly. Then after that, to increase, there is a sudden increase here. So basically, because you see these are the electrons from 3p and 3s. So they are in the same shell. So increase a little bit. Okay. So in a sudden, there's a big increase here because this one is from the inner shell, which is from 2p, and then from 2s. So in the same shell, there is not much increase, but between one shell and another shell, there is a big increase. So you have to see a trend in that way. So later we will practice some exam question which involve graph. So you have to understand it in that way first. Okay, now let's see. The first electron removed has a low ionization energy, as it is easily removed from the atom due to the spin pair repulsion of the electrons in the 4s orbitals. So they are talking about calcium again. Calcium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Okay, so to remove the first electron, so it is easy because two reasons. First, this is neutral. Second, spin pair repulsion. The electrons stay in the same atomic orbital, so there are spin pair repulsions. The second electron is more difficult to remove than the first electron, as there is no spin pair repulsions. No spin pair repulsion. Okay, so the second electron is where it is 4s1. It's 4s1, so no more spin pair repulsion. There is only one electron here. Okay, so more difficult to remove because no more spin pair repulsion, and second, calcium is already positively charged, which attract the electron at the same time. So the third electron comes from here. Okay, so I write down first. The first and second come from here. Then this is the third all the way until the 8th. So let's see. The third electron is much more difficult to remove than the second one, corresponding to the fact that the third electron is in a principal quantum shell, which is closer. This is closer. This is the third shell, closer to the nucleus. Compared to this is the fourth shell. So when it's closer, now that they are talking about the distance. So removal of the fourth electron is more difficult, as the orbital is no longer full, and there is less spin pair repulsion. Okay, no more less spin pair repulsion already, because it's not full anymore. Okay, so Let's see, exam tips. It is easy to remove electron from a full subshell as they undergo spin pair repulsion. It gets more difficult to remove electron from principal quantum shells that get closer to the nucleus as there is less shielding and an increase in attractive forces between the electron and nuclear charge. So these are the highlight on the of the same fact that we discussed just now. Okay, now see. Okay, let's see the information here. Energy is required to remove an outer shell electron as these involve breaking the attractive forces between the electron and the positively charged nucleus. Okay, so there are several factors which affect the magnitude of the ionization energy. Okay, so they are trying to explain why we need ionization energy is to break the attractive forces between the nucleus and the electrons. Okay, so which affect the ionization energy? First, nuclear charge. Nuclear charge, basically, nuclear charge, the nucleus attract the electrons. So you need to break that attraction. So that's why we need energy. Shielding. Shielding is repulsion from the between the inner shell with the outer electron. Shielding will make the ionization energy decrease. Shielding, repulsion. Okay. Nuclear charge will make the ionization energy increase. Okay. So this is what they are trying to say actually. So nuclear charge, when it is higher, ionization energy is higher. This one, what they are trying to say is, if the shell is getting more, then the shielding effect is getting more, then the repulsion is getting more, then the ionization energy is getting less. Okay, so they are talking about this actually. And they also show pictures here. So this one is attraction. Okay. Nucleus and outer electrons attract. So electron and electron, this is shielding effect, repel. Okay, let's move on. And we see here atomic ionic radius. The larger the radius, okay, straight away because we discussed this already. Okay, so basically, if the radius increase, then the ionization energy decrease. So it should be common sense here. Radius increase means the size is getting bigger. So when it's getting bigger, the distance is getting bigger, then at the same time the shielding is getting stronger, and then repulsion happens, and the electron can go away easily. Now spin pair repulsion we discussed already. So when spin pair repulsion happens, ionization energy decrease. Okay, so let's see this diagram. Summary of factors affecting ionization energy of atoms. So we have 4 factors. Nuclear charge. If the nuclear charge increase, ionization energy increase. Increase in shielding effect will make the ionization energy decrease. So this one will make IE increase. This one will make IE decrease. Small atomic or ionic radius. If it is small, then IE will be higher. Spin pair repulsion make ionization energy decrease. Okay, so let's move on. Okay, now successive ionization data can be used to, okay, let's say something like this. This is called from here. This is not counted. This is how many electrons are there. Okay, this is the successive ionization energy when you go across in horizontal. So you can see in a sudden that increased by 10 times, from 494 it become 4000 something. So 10 times increase. So that means this is from the inner shell. This is from the outer shell. So we can predict, we can predict something like that. This is, sodium. Sodium is 1s2, 2s2, 2p6, 3s1. The first IE involving removing these electrons, and then the second IE and so on come from these orbitals. Okay, so where they are closer to the nucleus. So that's why there is a big increase over here. So that's why when you see the big increase here, you can use it to predict or confirm the simple electronic configuration of elements. So you can see, oh, it should be like this because here to here there is a big change. Confirm the number of electrons in the outer shell of an element. Example, magnesium. How many electrons in the outer shell? So then you can count like this. 1, 2, this one double only lah. Double is still okay. In a sudden it increased 5 times. About 5 times, okay? So it increased about 5 times in a sudden. So that means these 2 electrons should be in the same shell. Then this is the inner shell. So we put it like this. This one, then in a sudden increase. This one, then in a sudden increase. Aluminium, these 3, then in a sudden increase 5 times to 10,000 already. So showing that sodium has 1 valence, magnesium has 2 valence electrons, aluminium has 3 valence electrons. So we can confirm the number of electrons or the number of valence electrons. Deduce the group 1, group 2, 2 valence, group 2, 3 valence electron, group 13. Okay, so by analyzing where the large jumps appears, large jump appears here, then that means there are 3 valence electrons. Okay, where the large jump appear and the number of electrons removed when this large jump occur, the electron configuration of an atom can be determined. So if there is a large jump after 3 electrons, that means there are 3 valence, and then we can predict the electronic configurations. So sodium, magnesium, and aluminum will be used as example to deduce the electronic configuration and positions of elements in the periodic table using their successive ionization energy. So we can predict group 1, group 2, and group 13. Okay, so finally, let's see here. Okay, so sodium, there is a huge jump from the first to the second, indicating that it is much easier to remove the first electron than the second. That means first electron is in the outer shell, second electron is in the inner shell. So outer shell, inner shell. So therefore, the first electrons to be removed must be the last electrons in the valence shell. Thus, sodium belong to group 1. So 1 valence electron, group 1. The last jump corresponds to moving from the 3s to the full 2p subshells. So that's why there is a last jump here. After removing the first electron, there is a last jump. So the huge increase happens in the second and third. So meaning that after removing 2 electrons, then there is the huge increase. So therefore, valence shell must contain only 2 electrons. 2 electrons belong to group 2. The last jump corresponds to moving from 3s to 2p. So aluminium, the huge increase in the third and the fourth. So third and fourth, after removing 3 electrons, so then that is a huge increase. So the 3p electrons and the 3s electrons are relatively easy to remove compared with the 2p electrons, which are located closer to the nucleus and experience greater nuclear charge. So removing these 3 is easier, so no huge increase in the first 3. Then the fourth one, that is a huge increase. So because this is closer to the nucleus. So this is due to weakened shielding effect. So once you remove these 3, right, the shielding effect getting lesser already because the number of shell decreases. So the last jump correspond to moving from the third shell to the second shell. So after removing 3 electrons, now you are going to the second shell already. Third shell, no more electrons. So quite complicated, but I hope you can see the trend. Now, finally, yeah. So exam tips here. Find the large jumps by subtracting the successive ionization energies from each other to identify when an electron has been removed from a different subshells. So you have to see where is the huge increase. Okay, so let's practice now.